Hello everyone. Over the years, we've learned a lot about space through various research. However, these studies have brought more questions along with the answers. For example, scientists have always wanted to know if there are other life forms in the universe. Nowadays, in the middle of the Milky Way, an unknown and strange signal has been detected. In today's video, we will discuss what this signal might be. If you're ready, let's get started. Starless alien planets. The more research scientists conduct about space, the more they find things that contradict the existing theories. Initially, we believed that all planets should be in orbit around some kind of star. However, recent discoveries show that there are planets traveling through space without orbiting any star. Lately, Kepler might have changed everything by providing more evidence for the existence of free-floating planets. From the data collected by NASA's Kepler Space Telescope, it was observed that some exoplanets roam freely on their own. Kepler gathered this data during a 2-month period as part of the K2 mission. Throughout these 2 months, Kepler observed an area consisting of millions of stars near the center of our galaxy every 30 minutes. While analyzing this data, scientists hope to see signs of rare gravitational microlensing events, where a prominent massive object bends the light of a more distant star or quasar due to gravity. During the analysis, some short-duration signals with lengths ranging from 1 hour to 10 days have been discovered. So far, only a portion of these signals has been understood. However, the data obtained from these 4 signals is consistent with the presence of planets roughly similar in mass to Earth. If there were a host star and a planet in orbit, scientists would receive a longer signal. Well, it is believed that these planets initially orbit a star, but are later pulled by a gravitational force, or a larger planet or object. Detecting these signals was quite challenging for scientists, because Kepler was not designed to examine outer planets or such a crowded star field using microlensing. Additionally, the telescope was quite old and couldn't produce images of the required quality. Instead, the instrument used a blurred view with numerous bright stars and asteroids. A researcher likened the study to searching for a firefly's single blink in the middle of a highway using a mobile phone. Scientists had only one chance before the signal disappeared. Therefore, they needed to develop a new strategy. Since the retirement of the Kepler telescope in 2018, researchers have turned to other telescopes capable of performing this task. Some of these include the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope. Both of them have the capability to detect signals from microlensing events that could be used to confirm the existence of these peculiar planets. However, remember that while these discoveries are exciting and intriguing, the existence of free-floating planets has not been conclusively proven. Fast radio bursts, FRBs, also known as fast radio bursts, are rare light bursts that last only a few milliseconds and have puzzled scientists for years. After being detected outside our galaxy, scientists embarked on various studies, working on this for 13 years. However, on April 28, 2020, 2 ground-based radio telescopes detected intense radio waves in the Milky Way, marking the first FRB detected in our galaxy. Although this FRB lasted only 1 millisecond, it was nearly impossible to miss. In short, the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, and the Transient Astronomical Radium Mission, known as STEER-2, determined that the FRB is approximately 30,000 light-years away from Earth. Normally, you need to point telescopes in a specific direction to capture an FRB. However, by chance, if the device is aligned in the right direction, you can capture an FRB. This discovery brought great joy to scientists because CHIME was not aligned in the right direction when it captured the FRB with 2007. Duncan Lorimer and David Narkevich discovered the first FRBs while examining data from the Parkes radio telescope in Australia. So, why were the first FRBs discovered at such long intervals? The reason is that FRBs are very distant and appear for very short durations. Normally, when astronomers discover something, they focus one or more telescopes on the object to examine it properly. However, they couldn't do this with FRBs because these bursts disappear in the blink of an eye. However, astronomers did not give up on FRBs, and they were able to collect enough information about light based on events recorded from outside our galaxy. Thanks to the research, we know that FRBs are bright radio light bursts that can last from microseconds to milliseconds. We have also determined that most of them are billions of light years away. However, the only unknown about FRBs is their origins and what they could be. Therefore, we can say that scientists made a significant breakthrough when they discovered the most energetic radio burst in our Milky Way in April 2020. Previous FRBs were billions of light years away, making it much more difficult to study them. But now that we have found light closer to us, we can say that scientists are closer to determining the origins of FRBs. Since then, astronomers have been summarizing their theories about FRBs, suspecting that light may come from small sources. Moreover, the fact that FRBs are both small and energetic could be related to neutron stars. However, the most plausible theory is that these phenomena originate from the remnants of supernovae with magnetic fields that are 5,000 trillion times stronger than Earth's magnetic field, and therefore, they are believed to originate from young neutron stars known as magnetars, which are referred to as the most powerful magnets in the universe. In fact, this is not just a theory. There has been extensive research into examining FRBs with magnetars since these suspicions arose. It is known that magnetars emit high-energy electromagnetic radiation, especially gamma rays and X-rays. Both of these are short-lived bursts, and there is speculation that during such a process, radio waves could be emitted. This theory suggests magnetars as the source of FRBs. The most recent FRB discovered in our galaxy was named FRB 2004-28 by astronomers, and it was found to originate from the Vulpecula constellation, where the galactic magnetar is located. This discovery was accompanied by an X-ray burst from the same region of the sky. However, this FRB occurred before the discovery of FRB 2004-28. It was also found to emit multiple X-ray and gamma-ray bursts, in addition to the known transient radio emissions from the magnetar. Telescopes observed X-ray bursts from the magnetar simultaneously with the fast radio bursts. However, to be sure, attention turned to the spherical radio telescope with a diameter of 500 meters, known briefly as FAST, located in southwestern China. This telescope calculated an FRB in the vicinity of the galactic magnetar, known as SGR 1935 plus 2154, called FRB 2004-28, which further confirmed the relationship between X-ray sources and fast radio bursts. In other words, it was a clue about how magnetization produces FRBs. However, scientists are not speaking so definitively for now and are continuing their research. So far, we have only been able to map distant planets that could support life, and none of them have shown any signs of hosting intelligent life forms. However, when scientists captured a space signal from the region of Proxima Centauri, the closest star to our solar system, everything changed. The discovery of this radio signal increased the likelihood of extraterrestrial life. So, where did this radio signal come from, and what conclusions have scientists reached? Proxima Centauri is one of the most fascinating star systems studied by scientists so far. It is the closest star to our Earth, located 4.2 light-years away from our Sun. This star is much smaller in size and mass compared to our Sun, and is situated in the southern part of the Centaurus constellation, discovered by Robert Innes in 1915. Proxima Centauri can only be observed with a telescope. Proxima Centauri has star bodies orbiting in its orbit, described as celestial objects resembling the solar system. Proxima Centauri, a dwarf star, has a mass of approximately 12.5% of our Sun and is 33 times denser than the Sun. Despite having very low brightness, Proxima Centauri is filled with high levels of radiation and randomly releases solar flares of considerable intensity. These explosions affect two exoplanets, Proxima Centauri b and Proxima Centauri c, orbiting around the dwarf star. Proxima Centauri, another exoplanet candidate, orbits at a distance of approximately 220 million kilometers from the dwarf star and completes its orbit every 5.2 years. However, the existence of Proxima Centauri d is still debated by astronomers worldwide due to its distance from the star. The presence of the other two planets has been confirmed and is under continuous investigation by astronomers and scientists. Proxima Centauri b, located about 7.5 million kilometers away in the orbit around the dwarf star, completes its full orbit in just 11 Earth days. With a mass 1.17 times that of Earth, this planet orbits within the habitable zone of Proxima Centauri and shares many similarities with our own planet. This allows for the possibility of atmospheric formation and ideal temperatures for liquid water formation on this exoplanet. Proxima Centauri is a radiant star and possesses a random electromagnetic radiation belt. Scientists have extensively discussed the potential challenges of solar flares that may make the habitability of Proxima Centauri b less likely. It hosts approximately 10 to 50 times more radiation on its surface compared to Earth. The high radiation levels on Proxima Centauri b can lead to increased oxygen and carbon monoxide levels, regardless of the planet's atmospheric composition. These elevated oxygen levels may facilitate the evolution of complex chemicals and organisms necessary for organic life. This idea was put forward by scientists who believe that Proxima Centauri b could have a vast atmosphere filled with organisms, and it was claimed to be the source of the recently emitted signal from the region. Cooling on the exoplanet could also lead to chemical reactions that could contribute to the development of life, and therefore, although it is still in the theoretical stage, it carries the possibility of hosting extraterrestrial life forms. However, Proxima Centauri b has the potential to be a planet similar to Earth, and when interstellar travel becomes possible one day, it will be the closest planet to Earth beyond our solar system. Although it may take thousands of years for such travel to reach the planet with any of our mobile vehicles or satellites, it revives our hopes of the existence of life beyond our solar system. Certainly, while spacecraft may not reach Proxima Centauri b in the near future, we continue to examine it from Earth using telescopes. Recently, a signal that could only be attributed to intelligent life was detected. In April 2019, a radio signal believed to have come from the Proxima Centauri region was detected. This groundbreaking listening candidate signal, referred to as BLC-1, was detected through the Breakthrough Listen project, an initiative established to search for intelligent extraterrestrial communication across the universe. The project received over $100 million in funding and involved thousands of hours of telescope observations at state-of-the-art facilities worldwide. Starting in January 2016, the program continues to be the most comprehensive search effort for extraterrestrial communication beyond our solar system. The signal was detected by the CSIRO Parkes radio telescope in the state of New South Wales, Australia. During the discovery, the telescope was observing the region where Proxima Centauri, the nearest star to our solar system, is located. Over time, as the telescope collected a large amount of data, scientists couldn't immediately detect the signal. At the end of each observation cycle, they had to filter hundreds of thousands, sometimes millions, of signals to detect unique technological signals that could potentially come from space. Furthermore, these signals must have two distinct features. First, they should be confined to closed frequencies, very much like radio broadcasts on Earth. This is a unique situation, because no natural process can generate such a signal, and if it's coming from space, it certainly raises alarms. Second, the signal's frequency should shift similarly to the Earth's motion for outer planets. During this special observation cycle, the telescope in Australia received more than 4 million different signals, and the team had to work on filtering out insignificant signals. the team managed to filter out most of the signals originating from Earth, leaving behind 5,000 different signals. The team later cross-referenced these signals with radio transmitters currently present on Earth, and eventually, only one unexplained signal remained. A team of scientists defined this signal as a unique technological signature, which emerged during a 30-hour observation period when the telescope was pointed exclusively at Proxima Centauri. The discovery of BLC-1 indicated that this signal most likely came from Proxima Centauri and had a different characteristic from the WOW signal discovered in 1977. WOW signal was a powerful narrowband radio signal discovered by the Big Ear radio telescope, which was the first instrument used in the search for extraterrestrial intelligence in Ohio, USA. The WOW signal appeared to come from the Sagittarius constellation, and it was the first sign of extraterrestrial communication beyond our solar system. The signal lasted approximately 72 seconds and has not been detected by any other telescope on Earth since then, including human-made sources. There are several hypotheses regarding the origin of the WOW signal, but none of them have sufficiently explained its source. Currently, it continues to be the strongest evidence of extraterrestrial radio transmission from outside our solar system. However, despite BLC-1 sharing similar characteristics with the WOW signal, researchers using the Park telescope needed to be sure that they eliminated other possible explanations for the signal's origin. Connecting a radio signal to extraterrestrial civilizations could be possible in cases where no other possible hypothesis can explain the origin of the signal. Therefore, a significant research effort was initiated to decipher the origin of the signal. Initially, the team began observing Proxima Centauri about 2 years after the first signal was detected in an attempt to replicate the observation conditions that led to the discovery of BLC-1. However, they could not find any evidence of a signal similar to BLC-1 in the Proxima Centauri region. The team then continued to investigate the possibility of a mobile transmitter that could explain the source of the signal. This transmitter could be any object such as trains, planes, helicopters, balloons, and other electronic devices capable of transmitting signals over long distances. However, even if one of the moving objects were the source of the signal, it could not explain why BLC-1 appeared continuously for several hours. The team concluded that a mobile transmitter could probably not explain the orbit that led to BRC-1 drifting for such a long time. In a statement to the press, the team said that creating a continuous path for the measured signal to continue as displayed would be extremely challenging. Additionally, while investigating the origin of the signal by examining satellites, the team had reached a similar conclusion. The reason is that satellites in low Earth orbit move too fast to generate signal shifts for such extended periods, and stationary satellites do not exhibit any shifting. So it was concluded that no satellite in orbit could probably generate the BLC-1 signal. Later, the team continued to investigate deep space probes such as Voyager 1 and 2 as possible sources of the signal. Probes are the only human-made signals that transmit objects in deep space. However, the team ruled out these probes from the list of signal sources because they were not aligned with any telescope and were not present in any region near Proxima Centauri. Finally, the team decided to examine the signal itself, and they noticed that it had a consistent and distinct shift known as the Doppler effect. The Doppler effect, named after the famous scientist and mathematician Christian Andreas Doppler, is the phenomenon where the frequency and wavelength of any physical entity exhibiting wave characteristics are perceived differently by a moving observer at different times or locations. This inconsistency indicated that the frequency was not caused by the motion of Proxima Be or any planet in the orbit of Proxima Centauri. The signal had its own frequency of 982.002 MHz and had an increasing Doppler shift instead of a decrease in frequency. This led the team to re-examine signals similar to BLC-1 in the data extracted from previous research, and surprisingly, they found 5 more signals similar to BLC-1. As the research continued, they discovered 27 more similar signals. At this point, scientists thought they had found the source of the signal. The signal frequencies were folding due to the interactions of common clocks and other digital electronic devices. and it appeared that Parkes' telescope, albeit in a new form, was detecting its own radio frequency interference. Scientists examining strange objects around the Milky Way discovered activity in the supermassive black hole known as Sagittarius A at the center of our galaxy. Furthermore, a peculiar group of objects was detected not far from the black hole. Normally, these objects appear compact, but during their orbits, which can last between 100 and 1,000 years, they elongate when they are close to the black hole. Going back to 2005, scientists had identified an object they named G1 at the center of our galaxy. Later, in 2012, they found a second object named G2. By 2014, G2 had been identified near the black hole. Initially, it was believed that G2 was orbiting along with the black hole, but it was later thought to be two stars that had merged into a single giant star and were hidden by a thick cloud of gas and dust. Recently, scientists have discovered 4 more objects named G3, G4, G5, and G6, which are similar to each other but have different orbits than G1 and G2. Researchers believe that all 6 objects are binary stars or star pairs that orbit each other due to the strong gravity of Sagittarius A. This suggests that star mergers may occur more frequently in the universe than previously thought. It is believed that the black hole could cause star mergers, and most of the stars currently observed may be the ultimate product of past mergers. The interaction between galaxies and black holes is evolving, and this situation is actually perplexing scientists. Therefore, they are putting in more effort to gain knowledge about this interaction. On the other hand, although these mysterious objects near the Milky Way appear quite similar, G2 is different from the others. This is because G2 hasn't stretched out like the others. Scientists believe that something must have kept G2 compact to survive its encounter with a black hole. It seems that there is an unknown effect at play with G2. Furthermore, the fact that these G objects are found near the Sagittarius, a star, which devours gases stripped from stars, suggests that these objects could be feeding the black hole. This is evidence that there is complete chaos, not only in the Milky Way, but also in other galaxies. Astronomers are still gathering information about G objects and continue to analyze them while searching for other celestial bodies. As a result, we can understand that there is much to be discovered in space. However, no one knows how long it will take to unravel all these mysteries. What do you think this signal could be? Don't forget to share your thoughts in the comments section. As for me, I am just lonely human until we meet again.